Hi everyone. I am Richa Gaur and I am a program manager at Azure Cosmos DB in Microsoft. Today I am going to talk about how to model and partition data in Azure Cosmos DB. So what is Azure Cosmos DB? Azure Cosmos DB is high performant, multi-model, highly efficient and globally distributed database. But for this presentation, we are going to talk about two things. So Cosmos DB is horizontally scalable. What that means is whenever you are interacting with Cosmos DB, you are interacting with a container, which can be thought of as a single logical resource. The resource is backed by a cluster of physical servers which have embedded storage and compute capacity. This is how we deliver unlimited throughput and unlimited storage capacity. The more servers you add into the cluster, the more storage capacity and throughput you get. Let's first talk about traditional relational databases. They enforce relational referential integrity and they also perform joins. Cosmos DB is a document database, which means that it doesn't have any schema constraint, and you can practically insert any kind of document into the Cosmos DB, which also means that you can't have any referential integrity and you can't perform joins between multiple documents. But why is that? The answer is simple because Cosmos DB is horizontally scalable, enforcing referential integrity and performing joins among multiple physical nodes is not only hard but it also has high performance impact, which essentially renders it useless. So the question is Cosmos DB suitable for relational workload? It sure is. Most workloads in Cosmos DB are actually relational. So how to think about modeling data in Cosmos DB? We actually have to shift the paradigm about data modeling and how we think about them in relational world. We need to change our approach and think of intuitive ways to model data. So let's take a concrete example. We are taking an example of a healthcare application, and it is a relational model which has multiple entities and multiple relationships. It has doctor entity, patient, appointment, prescription, test, report. So these are the operations that we want to perform in our app. These are fairly standard operations like create a doctor, create a patient, schedule an appointment, cancel appointment, find available slots for a doctor, get medical history of a patient, etc. So let's see how we perform these operations on our app with the data model. Let's look at this entity relationship diagram. We have doctor, which has slots. So let's assume that we insert next 3 months of slots in the table for each doctor. Now on these slots, appointment can be scheduled. So appointment and slots is going to have a one-to-one relationship. But the doctor can have multiple slots, so doctor and slot has one-to-many relationship. Now whenever appointment is scheduled, a patient is linked to an appointment. Now, but one patient can have multiple appointments, so it has a one-to-many relationship. Now, doctor prescribes prescription either to an patient, but it can prescribe prescriptions to multiple patients, so it has one-to-many relationship. Similarly, patient can have multiple prescription either by one doctor or by different doctors, so it also has one-to-many relationship. Now, prescription contains a diagnosis, what a doctor has identified or what he or she suspects, as well as test, what test he recommends to identify the problem. So a prescription can have multiple tests. A test will then have its report, which will contain the diagnosis. So test and report is do have a one-to-one relationship, but since a prescription can entail multiple tests, so prescription and test are going to have one-to-many relationship. So let's see how we are going to model this in Cosmos DB. Let's start with the doctor entity. For doctor, what are the operations that we want to perform? We want to create doctor, sometimes edit a doctor, and we want to find all doctors for a particular department. So doctor has an ID, a name, its date of birth, gender, department, and address. To start with, we will just transform this entity into a JSON document. Now, since the operations are fairly simple, this entity should suffice. Let's think of now comes the partition key. So what is partitioning? As the name suggests, is dividing data into chunks. So we divide data into multiple chunks. In order to divide data into chunks, we need to divide the partition key. The partition key basically defines the logical partition. So all those documents which have the same partition key will be part of the same logical partition. Logical partition is nothing but a group of documents in a container which have the same partition key. Let's take an example to understand this. We are creating a new container named my container, and we define its partition key as username. So all those documents which have the same username will reside within the same partition. So here in this example, Andrew, Deborah, Tim, Mark, Thomas, all of these are different usernames, and all documents which have the same username will reside within the same logical partition. Now, a single document in a container has a maximum size limit of 2 MB. But the good news is that we are also previewing a 16 MB document size limit for MongoDB API. And the maximum size limit for a logical partition is 20 GB. That means that when you are defining a partition key, you need to think of what is the maximum size of this partition is going to be. It should not increase 20 GB limit. When we are thinking of partitioning, we need to think that partition key should be such that your data is evenly distributed in the logical partition. What that means is that one of the logical partition, or like few of the logical partition, should not be cluttered with lots of document, and rest of the logical partition should not be empty. The data should be evenly distributed storage wise among the logical partitions. In this example, we have a hot logical partition where lots of data is in one partition and rest of the logical partitions are completely free. When that happens, you can basically surpass the limit of 20 GB for one document, one logical partition, and you have more compute and storage restrictions on one logical partition. We also need to think about the query patterns. The partition key should be such that your logical partition should receive an even number of queries or equitable distribution of queries among all logical partitions. We should not have one partition where all the queries are coming, or lots of queries are coming for that matter, and rest of the partitions are free, because your storage and compute are basically divided among partitions. So, for example, let's take a scenario where the partition key is let's say the date created, and we always query data for current date. In that case, the data would be evenly distributed because data is being distributed on the basis of date. So for each date, there is even amount of data or fairly equal amount of data. But since we are always querying on for current date, we will always hit the query on the current on the partition which has the current date. So there will always be a hot partition, and rest of the compute and storage is getting wasted. So in this case, username is the partition key, and we always query by partition key. So this basically satisfies both our storage as well as throughput scenarios. And we, whenever we query, we are always touching a single logical partition and in turn a single physical partition. One thing to note here is that one physical partition has a maximum size of 50 GB and it can contain more than one logical partition. So whenever we ingest data and the size increases beyond 50 GB, the logical partition splits into two different partitions. So one logical partition will stay in one partition and another will go in another different partition. So that's how a split happens in Cosmos DB. Now when we query from something other than partition key, our Cosmos DB is forced to touch all the logical partition because it is not aware of the documents where favorite color orange resides. So it has to actually touch all the logical partition and in turn all the physical partition, which leads to a significant amount of compute as well as physical network resources, and in turn it's a costly query. So it is always advisable to choose your partition key in such a manner that your queries are always touching one physical and one logical partition. Coming back to the doctor entity, we have queries like create a doctor, find a doctor, find all doctors for a department. Before talking about partition key, let's first understand what data this container have. This container contains data for the doctors or in a hospital. And if a hospital is big enough, it might have 1,000 doctors. But data for 1,000 doctors is still small enough to fit into a single logical container or even a single physical partition. The limit for a single logical partition is 20 GB, and for a physical partition it is 50 GB. So what partition key we should define? So we can either choose to not partition our data because it is small enough and we would want to query entire data in one go, or we can choose to define ID as the partition key because that way your logical partitions are evenly distributed. We would have one logical partition for one doctor. Or we can even define department as a partition key where we would want to query the data by department for all the doctors. Now for purpose of this exercise, let's assume that we define ID as our partition key, which seems a fair choice because our data is evenly distributed and we can query by doctor ID whenever we need to query. So for this example, let's look at the queries. So create a doctor is simple enough. You don't need you define the partition key. Find a doctor, you can query by doctor ID. It would be a point query. And for find all doctors for a department, oh, it seems tricky, right? So we would query by department, which is not our partition key. But when we look at the data, since it is small enough, it would still be within one physical partition, right? So when we query by department, our Cosmos DB will go and look at all the logical partitions and filter data by department. but all that data will reside within one physical partition. That means it has to go and query one physical machine. So this query will still not consume a lot of our cost, and it is still optimized enough for our use case. Now coming to slot, for slot we have ID, doctor ID, which determines for which slot this doctor is, for which doctor this slot is, slot date, start time of the slot, end time of the slot, and whether the slot is free or not. So we just create a similar JSON document. Now the queries are like create a slot for a doctor, get free slots for a doctor. So what should be the partition key here? Now clearly we are creating slot for the doctor, and we are always querying slots for the doctor. So it makes sense to define doctor ID as primary partition key. Coming to appointment, we have ID, patient ID, slot ID for which this appointment is booked, and the date on which this appointment was created. We have queries like create an appointment, reschedule an appointment, cancel an appointment, and list all appointments for a doctor. So we start again with defining the entity as the JSON document. Before we talk about partition key for appointment, let's look at the relationship between slot and appointment again. As I mentioned earlier, it's a one-to-one mapping. So how do we represent a one-to-one mapping in Cosmos DB or in a NoSQL world? So there are two options. Either we can embed appointment in a slot, or we can reference slot ID in the appointment as we were doing in the entity relationship diagram. So the general guideline is we should embed when there is one-to-one relationship or one-to-few relationship, and we should reference when there is one-to-many relationship and or many-to-many relationship, because there are too many documents which are not going to fit into a single document. And apart from this, a general criteria is that whenever two items are queried together or updated together or created together, they should belong to the same document. And inversely, like if the documents are like independently created, independently updated, or even independently queried, they should reside in different documents. So these are not strict rules, these are just guidelines. So for our case, we have one-to-one relationship, and we we are going to query an appointment and slot together. So it makes sense to embed slots and appointment together into one document. So for starter, we embed the appointment document into the slot document. And to improve it further, since it is one-to-one relationship, we can directly map patient ID and date created into the document. And we don't require is free field, because if the patient ID exists in the document, that means that the slot is booked. And yes, the prime partition key is going to be the doctor ID, because all the operations are determined for a particular doctor. But the question comes, how to return patient and doctor name. So whenever we want appointment information, we would want to see what is the doctor name and what is the patient name. So whenever an appointment comes, you want to call the patient name and you want to see the doctor name to inform the patient. So in order to do that, we'll have to query patient container to find the patient name. Similarly, for doctor name, we'll have to query the doctor container. This means that we are going to have 3 queries for single operations. which is pretty bad than relational workload, because in relational workload we could join these three tables together and get the result in one single query. Now you're wondering, here are my joins. So in order to overcome this shortcoming, we introduce denormalization in non-relational workloads. So the idea is that we optimize our data models such that whatever data we need is ready to be served in a single document. Why we do that is because in earlier days we used to normalize data. We used to do 2NF, 3NF normalization, and basically optimize on storage, because storage used to be costly at that time. Disk used to be costly, but now storage has become really cheap as compared to compute, and time is of very high high importance. So we cannot compromise on time, but storage has become really cheap, so we can compromise on storage. So we can duplicate the data in order to get the result faster. So what we do is we embed doctor name and patient name in the slot document itself. So whenever we query for an appointment, we get the entire data in one single query. So how the query look like now is list all appointments for a doctor is simple. Select star from slot where doctor ID equals to whatever the doctor ID is. So it's a single partition query. Your query is going to touch only one logical and physical partition, and this is as optimized as it can be. Next query is find available slots for a doctor in a department for a given period. So we are querying by doctor ID, and we are touching a single partition, but there can be hundreds of slots for a partition, and we are filtering those slots by the given time period when we want to find the slots. So this is touching a single partition, but there can be hundreds of documents, and it might take further time doing sequential scan on those documents. So we can improve it further by introducing index. Index in Cosmos DB is not very different from what is in relational workloads. So it's pretty similar. So Cosmos DB defines a default indexing policy where all the documents in the all the fields in the document are going to be indexed by default. So this is what a default indexing policy looks like. In the included path, we defined path as /star, which means all the fields are going to be indexed. And in excluded path, we defined whatever fields we need to exclude. So by default, e-tag is a system property of Cosmos DB, which is not indexed. Now, this is pretty great, right? You don't have to worry about indexing. You don't have to worry like whenever you add a new field, whether it is going to be indexed or not. You don't have to worry what index you have to create, what index you have to update. So from maintenance perspective, it's quite great, but it also has a downside. Because all the fields are going to be indexed, it is going to take a long time while writing or updating the documents, because all those index are going to be written at the time of writing the document. Also, since all the fields are going to be indexed, the size of the index is going to be huge, which can basically add on to your storage cost. So this write latency and storage cost might not be desirable in a lot of scenarios. So Cosmos DB provides a way to optimize or customize your indexing policy. So we customize our indexing policy by including doctor ID, because that is the partition key, and that needs to be indexed, and date created, since that's what we are querying on. So by creating an index on date created, we can improve our query performance. And rest of the things we are not including, and we are adding them to excluded paths so that we don't create any additional indexes. Coming back to slots and appointments, we have create an appointment, cancel an appointment, reschedule an appointment. So all of these queries involve first fetching the document and then updating the appointment information in them. So it's a replace operation or an update operation in Cosmos DB. Which involves writing the document, updating the document again. Now that can be a little bit costly. So Cosmos DB has released a new cool feature of Patch API, which lets you define what operations you want to perform, what operations you want to perform on the document. You can define a list of operations that you need to do in order to update the document. That can be adding a new field, deleting an existing field, or updating the value of an existing field. So you can define all those documents within a single JSON object, and that will be part of the patch API request. So you do not need to send the entire document on the wire in order to update the documents. So that's how we can we can perform all these operations. Now coming to patient is again fairly simple. It has ID, name, DOB, gender, and address, and we can directly convert that into a JSON document. Talking of partition key, we have operations like create a patient or edit a patient rarely, which would happen rarely. So we can reasonably define partition key as ID, which would basically create a lot of logical partitions for each patient, and thus evenly distribute data among logical partitions. Coming to prescription, we have ID, patient ID, doctor ID, date created, and diagnosis. So we can convert that into a JSON document. Test, again, we can directly convert into a JSON document. Similarly, for report, we have ID, test ID, or test date, report date, and diagnosis. Now, before talking about partition keys, let's first talk about these relationships. So test and report have one-to-one relationship, as we earlier talked about. So we can, by the same logic, we can embed a report into the test document. So now we have ID, name, test date, report date, diagnosis of the report, and the prescription ID this test and report belong to. Looking at the relationship between prescription and test and report, prescription has multiple tests, but if you look closely, any prescription can have only a few number of tests. So in worst case scenario, we can have at most like 10 tests defined for a particular prescription. So we can fairly assume that a test and report can be embedded within the prescription document. When we talk about the query patterns, we have queries like get medical history of a patient. So that requires getting the prescription as well as all the test and report associated with that prescriptions. So it does make total sense to include them in a single document. So now we have test as a list passed into the prescription document. Talking about partition key, since we are always querying for prescription for a particular patient, it makes sense to create patient ID as partition key. So we have queries like create a prescription, which would be again for patient ID, get medical history of a patient again by patient ID, and get medical history of a patient for a particular doctor that would still be on a patient ID and queried and filtered by a doctor. Now, whenever we talk about prescription, we also need to get additional details like doctor name and the patient name for a particular prescription, so that whenever a medical practitioner is looking at a prescription, he can get a sense of which doctor recommended what and get the patient information as well. So we are again embedding patient name and doctor name into the document in order to get the entire data in a single query. This is again denormalization, which is a very common practice in NoSQL world. If you look closely at these two documents, patient has ID as a partition key, which is patient ID, and prescription has again patient ID as the partition key. Now, if you look at queries, we want to query patient information and its medical history. So, can we put these two different documents in the same container? Is that even possible? Mixing entities in the same container, yes, it is possible in Cosmos DB. We talked about the schema-free, schema-agnostic nature of Cosmos DB, so we can technically put two different type of documents in the same container. Why it is suitable in this particular case? Because they share same access pattern. Whenever we want to query for a patient, whenever a doctor wants to query for a patient, he wants to see his medical history, which is basically the prescription document. So we want to query them together. And they also share the same partition key, which is a technical requirement for Cosmos DB container. So essentially, adding them to the same container makes total sense. So we add these two documents into the same container patient. But how do we differentiate between these two containers? So we define a field as type, where patient document will have type patient and prescription document will have type prescription. So this is how a logical partition will look like. There will have a single patient document and multiple prescription document for a single patient ID. How would the queries be? So for example, list all prescription for a patient would be select star from C, where C.patient ID equals to patient and C.type equals to prescription. Similarly, if we want to query for patient, we can put C.type equals to patient. This will again be a single partition query. Similarly, for prescription by a single doctor would be C.type equals to prescription and C.doctor ID equals to some doctor. So this is what our Contoso Hospital schema looks like. So we have a patient container which has primary key as patient ID. It has two type of documents, the prescription document and the patient document. Then we have doctor container, which contains information about the doctor. It is a very small container which contains data of all the doctors in the hospital, and its primary partition key is ID. So essentially, all the documents in the doctor container are going to reside on single physical partition. For slot, we have one container. We have embedded slot and appointment entities into a single document because of the one-to-one relationship and similar access patterns. and we are going to store the next 3 months of slot data into the document. So we have another feature in Cosmos DB where you can define TTL on the document. So whenever we are inserting a document into the slot container, we can define a TTL of 3 months. So whenever 3 months passes, the document can get deleted by its own, and the container will always have fixed amount of documents. So its size is fairly constant, and its access pattern is fairly clear. So this is how the Contoso Hospital is going to look like. Next, we are going to talk about billing model in Cosmos DB. Billing in Cosmos DB is a function of two parameters, storage and throughput. Storage cost is pretty cheap in Cosmos DB. It is $0.25 per month for 1 GB for one region, and it is for standard transactional store, row-oriented store, and for column-oriented store it is $0.02 per month for one region. Another parameter is throughput. Throughput is represented as request unit in Cosmos DB. Request unit is a rate-based currency. For example, you consume 1000 RUs per second. It basically abstracts out the physical resources like memory, CPU, IO per second for performing a request. So whenever you perform an operation in Cosmos DB, it consumes a certain number of RUs. For example, a point read in Cosmos DB consumes 1 RUs always. So like that, all different operations will consume certain number of RUs, and you will be charged on the basis of these RUs consumed. There are two ways to configure RUs for a container. Let's talk about that. There are two ways to configure RUs in Cosmos DB. The first one is manual. In manual provisioning, you have to specify the amount of request unit your container might consume. So you have to evaluate that beforehand and specify that value while creating the container. This kind of provisioning is suitable for constant workload where your traffic pattern is predictable and you can optimally utilize the container resources. Another option is autoscale. Autoscale lets you consume between 10 to 100% of configured throughput value so that your container can scale up and down based on the number of requests or the requests coming into the container. This type of provisioning is suitable for variable workload where your traffic pattern is unpredictable and you have highs and lows throughout the day, so that your container can take care of scaling up and down the resources based on the requirement. The great part of autoscale is that you only pay for the amount of RUs that you have consumed, while in manual you have to pay for the configured value whether or not you are consuming it. Now, in both of the cases, if the number of if there are requests which are consuming more than the 100% configured value, then your requests will be throttled and they will be retried again from the SDK client. See how request unit works in Cosmos DB, how request units are consumed based on your queries in Cosmos DB. Hey, so let's look at a demo to see how request unit works in Cosmos DB. We have Contoso Hospital database, and in this database we have different containers like doctor, patient, and slot. Let's look at the doctor container. This container is partitioned by the ID, which is the doctor ID. So this document looks pretty similar to what we have seen in the presentation. Now let's try to query on this container. We wanted to list all the doctors in a departments. So we can see that more than 100 doctors are available in gynecology. Let's see how many request units were consumed in performing this query. So we can see that 10.16 RUs were consumed in performing this query, and 153 doctors are available in this particular department. Look at another container, Doctor 2. This container is now partitioned by department. Now let's try to query in this particular container. So see here, the request charge is again 10.16 RUs, and we have same 153 documents. Now why is that? We have partitioned one container by department and another container by ID, still the request charge is same. The reason behind that is, since we have a limited number of documents in this container and the total size of this container is less than 50 GB, which is the size of a physical partition. So all the documents reside within the same physical partition. So when we query in this container, Cosmos DB touches only one partition, and hence the cost of querying is same in both the scenarios. Let's move on to another container. This container is partitioned by patient ID. So we have ID, patient ID, name, DOB, gender, address, and type. If you remember, we had inserted two different type of document in the patient container. One was the patient type document and another was prescription type document. Now let's look at the prescription document. So this is an example of prescription document. We have all the fields, and then we have a list of tests recommended in this particular prescription. So now let's try to query in this container. We wanted to get the medical history of a patient. So let's query on that. Sorry, I had put the wrong spelling. So we have 29 prescriptions for this particular patient. Let's look at the request charges. So we have 4.48 RUs for this particular query, which is pretty fine. Now coming to slot container. We have slot, and this container is partitioned by doctor ID. So let's try to query in this container. For slot, we wanted to see available slots for a doctor. So let's try to query that. So for this particular query, 11.83 request units were charged. Now let's look at another example where we have slots container and it is partitioned by the department. Let's try to run the same query here. The request charge in this case is pretty high. It's 37.04 RUs, and in previous case it was 11.83 RUs. So it's which is pretty high. The reason behind this is that when we are querying by doctor ID in a container which has partition key as doctor ID, then in this particular case, the query is query is going to touch only one logical partition and hence in turn one physical partition. But in this particular scenario, where the slots are partitioned by department and we are querying by doctor ID, so what happens is, since the Cosmos DB doesn't know which particular logical partition has this particular doctor ID, so it goes and tries to find out this doctor ID in all of the logical container which can reside in different physical partitions. That's why it is taking such high request charge. So basically, we have to determine our partition key in such a way so that our queries are optimized and hence we can save on RU cost. Coming back to Contoso Hospital, we can now take a decision on how to configure request units in Cosmos DB. So in Contoso Hospital, we have variable workloads because there are more patients in OPD timings and lesser in nights. There are also seasonal workloads, like when you have whenever season changes, there is seasonal flu. Sometimes there is dengue, flu, and we saw there was a huge spike during COVID season. Sometimes there are unnatural bursts, like during natural disaster or man-made disaster. For example, there is a fire in a building and your hospital is the nearby hospital in the surroundings, so you get a lot of incoming patients in a very short amount of time, which is hard to handle at the moment. So we have two options to configure throughput. Either we can do it manually or we can do it as auto scale. Based on the kind of workload that we are dealing with, auto scale seems a better choice. But what to do about these spiky workloads when in the case of disasters? Cosmos DB have you covering. Now we have burst capacity is a feature which allows you to consume your previously unconsumed capacity in Cosmos DB. It is compatible with both manually as well as auto scale configured containers. So in Cosmos DB, when you configure throughput in a container, it is actually distributed among all the physical partitions. So let's say you have configured 10K RUs for a container, and let's assume that your data is distributed among 5 physical partitions. So each physical partition will get 2000 RUs equally. So whenever a request comes to a physical partition, you can only consume up to maximum of 2000 RUs at that particular moment. So burst capacity is actually useful when you have physical partitions which have a small amount of RUs, which is the case in our Contoso hospital because we have smaller workload and smaller data. So if you have physical partitions which has less than 3000 RUs per second, you can enable burst capacity to ideally accumulate the unused capacity and utilize it at the time of spike. So this lets you handle the spikes and avoid the throttles. So let's look into some of the details of burst capacity. It allows you to accumulate 5 minutes of unused capacity, which means that you can accumulate a maximum of 3000 RUs per second for the last 5 minutes. This is the maximum value that you can accumulate. So for example, let's say a partition has 100 RUs per second and it was ideal for last 5 minutes. So we have 300 into 100, that is 30,000 RUs accumulated, but we can at max consume 3000 RUs per second. So we'll have next 10 we will have 3000 RUs for next 10 seconds, which will help us address the burst in the request. So in this graph, we have 1000 RUs which is manually configured, and we have this orange line which depicts the real-time usage of RUs in this particular container. So as you can see, most of the time we are consuming 500 RUs, and but after between 545 to 546, we get a burst, and we are able to consume around 2000 RUs for next 1 minute. So actually we are able to consume more than the configured amount of RUs, which is not possible. So with burst capacity, we were able to consume this high amount of RUs for 1 minute. And when the amount of burst capacity has been consumed, we are back to the normal rate of RU consumption. So this allows you to go beyond the configured value of throughput, and you are able to handle the spikes and basically avoid the throttles which have been there if burst capacity was not enabled. This is another graph which shows consumption of provision capacity and burst capacity. So for most of the time, you are only consuming this blue line, which depicts the provision capacity. But for momentarily spikes, you are able to consume burst capacity. So in this case, you are able to consume 110K worth of RUs, while normally you are only consuming 40K RUs. So with burst capacity, you are able to handle such kind of scenarios and avoid throttles in Cosmos DB. So we have talked about manual provisioning, auto scale provisioning, as well as burst capacity. So based on your particular requirements, you need to evaluate your queries, you need to evaluate your access patterns, your amount of storage that you are going to consume, and based on that, you can use our calculator to estimate how much request units you need to configure. And if in case your traffic pattern is not predictable, to let you make that choice, you can go along with auto scale provisioning. So based on your requirements, go ahead and choose any of the options, and let us know the feedback.